Hi everyone, we are Group 25 and our topic is prediction of crop yield using machine learning model. Our group members are Teng Zhen Chi, Tan Zhong Ta, Li Zhongyang, Li Qi, Chong Wei, and Tan Yan. We are going to apply machine learning models that uses label data to solve the problems with the aid of physical data set to train predictive models. The models are aimed to predict the yield of the crops whether it meets the need of the area. By predicting the crop's outcome, it could assist the farmers in making informed decisions to prevent unnecessary loss and thus increasing the agricultural productivity. The research goal is to develop an accurate machine learning model to predict crop yield, to improve agricultural productivity and sustainability, and to reduce hunger by making food accessible to all. On the other hand, our research objective is to explore machine learning models that is able to accurately predict the crop yield and to identify the potential improvement that can be made to the crop yield prediction model by applying emerging technologies. Besides, our objective also includes using pre-processing and tuning algorithms to optimize the performance of the machine learning models. We have studied a few related works regarding crop yield prediction. The first one we studied is an article published on 2023. The dataset that they use is crop yield prediction in Rajasthan. The dataset contains 3,624 rows and 7 columns. We also studied an article using crop yield prediction of soybean crop in USA dataset, which contains 395 features and 25,345 samples. Besides, we studied an article using a dataset of creation of corn yield from USDA and analysis with a total of 321 features. Lastly, we studied an article using dataset of the historical yield data of the US corn belt and planting progress data from NSS, daily weather data from IEM, and soil data from SSURGO. They have 10 features with 20 rows. This is a few articles. One of the pre-processing techniques applied include replacing or imputing missing values either 0, average value, or even mean values. User apply encoding categorical data as it gives flexibility in performing a regression analysis that is compatible with the dataset used. Besides, they apply feature scaling that is to normalize the range of each feature in the given dataset, and features reduction that is to reduce unused or unnecessary features to keep the data even more organized and clean. Moreover, they also use a vast scaler that is to remove the median and scale the data range according to the quantile range to achieve quality results. The result shows that applying different methods in scaling features could impact the results and the machine learning models, thus we must compare them and when we apply them. Lastly, they apply data splitting that to train a machine learning model and allow them to evaluate the performance in different data. Hence, the model can make predictions accurately.
Hi, I'm Cheng Tat. Now I'm going to talk about the model used in related works. Multiple models such as random forest, supervised machine, lasso regression, XGBoost, and basic ensemble method are utilized. Both lasso regression and random forest were used in 2 studies, indicating a variety of models can be applied. So, in the study of Jajaria, random forest, supervised machine, and lasso regression outperform deep learning models in terms of accuracy. LSTM, long short-term memory, is noted to be more suitable for larger dataset for better prediction. In the study of Oikonomidis, he used extreme gradient boost and combined CNNs with RNNs or LSTMs. These advanced models generally outperform individual models, but the implementation requires strong fundamental and knowledge in machine learning. In the study of Shah Hosseini, it proposed 2 novel CNN DNA ensemble types for predicting crop yield. It used BM generalized ensemble method, GM, and stack generalized ensembles. The novel ensemble types, heterogeneous and homogeneous, outperform benchmark ensemble, with homogeneous giving the most accurate prediction. In the study of Sayara, Samira, Sajid, it constructed linear regression, random forest, and optimized weighted ensemble models. XGBoost, average weighted ensemble, and optimized weighted ensemble achieve similar R2 scores, 0.75, but different RMSE score, 1.00, 1.01, 0.99 respectively. So for the gap analysis, which machine learning model would have the best overall performance in predicting crop yields? Does applying hyperparameter on the model improve their performance? Does robust scaler in pre-processing improve the performance of the model? So next, I move on to the scope of research. We are aiming to investigate the performance of the prediction models by implementing removing missing values, encoding categorical values, and data splitting. We test the performance of research and cost validation by implementing it and improve it. Evaluating the model of lasso regression, random forest, and linear regression using R2, MSC, RMSC, and MAE. Thank you.
Okay. In our data set, it includes 10 columns and 7,929 rows. It contains both categorical data and numerical data. In data preparation, we handling missing value first. We use isNav function and sum function to identify missing value and drop nav function to remove them. After that, feature selection. We remove state name as it does not affect result. We also use season, crop, temperature, humidity, and soil moisture as independent variable. We added a crop yield as the dependent variable, calculated by dividing production by area. After that, in encoding categorical value, we use target encoding to convert categorical value into numerical value, ideal for unique variable like crop. This method prevents the dataset from expanding with many columns, unlike one-hot encoding, but require cross-validation to avoid overfitting and data lag. Next is train test split. We divided the data set into train and test set. The training set learns data pattern and relationship, while the test set validate and evaluate the model. Next is 3.3 model. In linear regression is a simple, interpretable model for analyzing relationship between variables. It's easy to implement and serve as a baseline for comparing more complex model. It helps us understand how features influence our target variable, but work best with linear regression. In Lasso's regression is a simple and effective for linear relationship, especially when dealing with multiple independent variables. It's easy to implement and interpret, making it a variable tool in our analysis. Last but not least, in random forest combine multiple decision tree for a single prediction, handling complex datasets with high accuracy. It reduces overfitting and chance generalization and is resistant to data noise, making it a robust choice. That's all. Yeah, thanks.
The following is model evaluation. First is R-squared, coefficient of determination. It determines the proportion of variance in the dependent variable explained by the independent variables. It indicates how well the dataset fits the model. The second one is MSE, mean square error. It measures the average of the square errors and identifies significant errors. The third one is RMSE, root mean square error. The extension of MSE by taking the square root. It evaluates model performance by indicating how data points are spread around the best fit line. The lower RMSE indicates data points are closer to the best fit line. The last one is MAE, means absolute error, the average difference between predicted and actual value. It's straightforward and easy to understand, not as sensitive to outlier compared to MSE. The following is the summary of methodology. Next, we proceed with initial EDA. First is data pre-processing, dropping row with null values. The figure demonstrates the process of handling missing data in the dataset. The missing values in the dataset are first checked with df in null sum. If found 59 values to be missing from the column production, then we use function df drop null was applied to drop such rows and visualize the dataset with no missing values. The following is dropping duplicate rows. The figure illustrates the procedure for identifying and removing duplicate rows in the dataset. First, we use df.duplicated function to identify 3,180 duplicate rows. These duplicates are then removed by using df-throw duplicates in place equal to true. Next, we handling outlier. The figure shows the method for detecting outliers in the numeric columns of the dataset. Using the Algebra method, the counts and percentage of outliers in each column are displayed, indicating significant outliers in temperature, area, production, and yield. Next, we remove outliers. The figure presents a remove outliers Algebra function. It is designed to remove outliers from numerical columns using the Algebra method. The clean dataset is then returned and applied to the original dataset to ensure a more robust analysis. Next, we check outlier in the clean data frame. After the removal of outliers, figure shown checks for remaining outliers in the clean data frame using the same Algebra method. The data is now more consistent and reliable for further processing and modeling. Hence, we do target encoding. The figure demonstrates target encoding for the categorical column, season, and trope, where the mean yield for each category is calculated and mapped back to the respective categories in the shown data frame. The result shows the first few rows of the encoded data frame with categorical variables replaced by their mean yields, making the data more suitable for machine learning algorithms. Next, we do data splitting. The dataset has been split into training 80% and testing 20% sets. Next, we use a matplotlib to generate scatter plot to visualize the relationship between humidity and yield for both the training and testing sets, with training data points in blue and testing data point in red. The last one is feature selection. This is the process of feature selections. We utilize recursive feature elimination RFE with a linear regression model to identify the most significant features from the training dataset. The RFE support must identify relevant features in the training data, including crop year, season crop, temperature, humidity, soil moisture, area, and production, which were printed as outputs.
Okay, now I'm going to continue with the descriptive EDA. On the left side is the basic info of our data set, and on the right side is the summary of the statistical data, which consists of mean, standard deviation, minimum, and maximum. Continuing with the data visualization, this code shows the distribution of categorical columns by its nut counts. These are some samples of the distribution graph. And continuing with the distribution of the numerical column, this code is used to code it, and these are some samples like the crop year, temperature, moisture, area, humidity. And moving on with the KDE plot of the numerical columns, this graph shows the distribution of crop year, and following with temperature and humidity. There are some plots that are not shown in these slides, so we're going moving on to the box plot. This box plot is used to identify the outliers in the numerical columns, such as temperature, soil moisture, and etc. And this is the correlation matrix of the numerical columns. It shows the relationship between the numerical features The more redder one is indicating a higher correlation, and the blue ones are indicating a lesser correlation with the another features. Okay, moving on with our linear regression, this is a baseline model which we use linear regression model and fitted it with the training set. On the left side is the typical value with the training set, and the right one is the test set. This is a scatter plot using the test set. The blue one is the predicted value, and the green one is the actual value, where the red dotted line is the best fit line. With a hyperparameter, we created a parameter grid that includes fit intercept and positive. And the grid search uses fivefold cross-validation with a linear regression model, parameter grid, and MSE as the scoring matrix. The grid search is then fitted with the training set, and the best parameter achieved is used to predict the yield of crops. This is the performance evaluation, which is quite similar in MSE, RMSE, and R2 score. However, it has a better performing MAE value. The performance evaluation is similar, thus the plotting is also likely to be similar with the baseline model. Moving on with the robust scaler, we initialized a robust scaler and fitted it with the test and trend set. Then we fit the X-train scale and X-train with the linear regression, predicting the value using the S-test scale. This is the performance of the model, and it's exactly same as the baseline model, thus the plotting is also exactly the same as the baseline model. So, summary of the linear regression. Both the baseline linear regression model and the linear regression model with robust scaler has the same performance, showing that robust scaler does not improve the performance at all, while the hyperparameter tuned linear regression model shows a better score in MAE, indicating that it's the most accurate model in these three models. I'll pass it to the next person.
In addition, another modeling is lasso regression model. Lasso regression model initialized with a regularization parameter alpha which set to 1.0 and a random state which set to 42. The model is then trained by using the training data which is coded as H-train and Y-train. The figure shows that we are using training data set to make predictions by assigning Y-predict with error model predict H-train. Then we evaluate the model using the evaluation parameters which are MSE, MAE, RMSE, and R-squared. This is the result of MAE, MSE, RMSE, and R-squared in the training datasets. Similarly, this is a result of MME, MSE, RMSE, and R-squared in the testing datasets. Next, the figure shows the relationship between actual values and the predicted values. The blue dot represents the predicted values, while the green X represents the actual value. The red dashed line represents where the best fit line with the predicted value matches the actual values. It is indicating that most of the predicted values are close to the actual values, demonstrating the model accuracy. The following is lasso regression with hyperparameter tuning. Hyperparameter includes alpha values which are 0.001, 0.01, 0.1, 1, 10, and 100. It determines best regularization for error model. Fivefold cross-validation use. The parameters which are verbose equal to 2 and just equals to -1 use. It fit with training data. We find optimal parameters by using alpha value to reduce overfitting and enhance performance. We extract best parameters and estimator. We evaluate model with training data and testing data. We use evaluation metrics for assessment. Here is the result of MAE, MSE, RMSE, and R-squared for both training and testing datasets. As we can see, the best parameters is alpha equal to 100. This the figure shows that relationships between actual values and the predicted values from the hyperparameter tuned R model. The correlation shows that the performance of the hyperparameter tuned model is like the baseline model, indicating no significant improvement of impact from tuning. The following is lasso regression with robust scaler. We initialize robust scaler to scale the dataset. We apply fit transform on training data and apply transform on testing data. We initialize random error model. We fit the model with scaled X-train, scale, and Y-train. We use scale data for both evaluating training and testing datasets. This is the result of MAE, MSE, RMSE, and R-squared for both training and testing datasets. The figure shows that the relationship between actual values and the predicted values from the robust scalar error model. The comparison shows that the performance of the robust scalar model is similar to the baseline model, indicating that no significant improvement from impact from tuning. Here is a summary of lasso regression. The comparison of three linear regression models, which are baseline with hyperparameter tuning and with robust scalar, shows minimal differences in performance. This indicates that neither hyperparameter tuning nor scaling with robust scalar provided significant improvements over the baseline model.
Now I'll talk about the random forest modeling. First, we build the baseline model. We first initialize the random forest regression model and set the n estimator and random state to 100 and 42 respectively. Afterwards, we train the model using the X-train and Y-train. Next, we use the model to make prediction using the training dataset, and we evaluate it using MAE, MSE, RMSE, and R-squared. And here are the scores. In this slide, we show that we use the model to make prediction using the testing set, and overall the performance is worse than the one we use training set. And here is a figure where it shows the relationship between the actual value and predicted values. The blue dot represents the predicted values, and the green dot represents the actual value, and the red dashed line represents where the best fit line is. The figure has shown that most of the predicted value is close to the best fit line, which means the model is quite accurate. And here is the hyperparameter tuning for random forest. And here are the hyperparameters that we use, including n estimator, max depth, mean sample leaf, max features, mean sample split, and bootstrap. And for the grid search CV setup, we use 5-fold cross validation, and the parameters we set verbose for 2 and n jobs for -1. And here are the best as parameters for the hyperparameter tuning. Afterwards, we evaluate the model using training dataset and testing dataset. And just like the baseline model, the testing dataset has the worst performance than a training dataset. Compared to the baseline model, there are more predicted values that are further from the red line. This means that this model is less accurate than the baseline model. Now, this is the random forest with robust scaler. We first initialize the robust scaler to scale the dataset, and we apply fit transform on training data and a transform on testing data. Afterwards, we initialize a random forest model and fit the data with scale, X-train data, and Y-train. Afterwards, we evaluate the model using the same metrics. Here you can see that the performance for both training set and testing set is basically the same as the baseline model. You can also see that from this figure, because the figure is very similar to the baseline model, which means both of them have the same performance. As a summary of implementation and result, we first conducted data processing and EDA at the following sequence, which is removing row with no value, removing duplicate row, checking and removing outlier, applying target encoding, splitting dataset, and lastly conducting feature selection. Afterwards, we conduct a descriptive EDA, and we start to conduct the experiment for all the machine learning model. For the RF model, the baseline and the one with robust scalar has the best performance. For lasso regression model, the model with hypertuning performs slightly better than the rest. Same goes for linear regression, where the hypertune model has slightly better performance as it achieves a lower MAE score of 74.9. Overall, the best baseline RF model and the RF model with robust scalar has the best performance compared to all of the other models. Now we'll talk about analysis and recommendation. First, we will reinstate the problem statement and summarize the approach that we took. As stated in section 1.0, many people throughout the world are starving. The primary purpose of this project is to create an accurate machine learning model for predicting crop yield, as well as using pre-processing techniques and hyperparameters tuning to improve the machine learning models. We first import required libraries and dataset. Afterwards, we perform EDA and pre-processing and splitting the data into testing and training set. Afterwards, we conducted data visualization, and finally, we conducted the experiments and we evaluate the performance of each experiment. Now we'll talk about model comparison. On the left, you can see the summary of all the models that we have conducted. On the right, you can see the benchmark models that we get from the related works. First, the benchmark RF model is significantly better in MAE and RSME compared to the models that we built. In terms of R-square, all the RF model from both tables has similar score, which indicates all the RF model has higher proportion of variance. Next, the benchmark lasso regression model is slightly better than lasso regression model that we built in terms of MAE and RMSE, indicate that the benchmark lasso regression is more accurate, but all the lasso regression model we built has better R-square score compared to the benchmark lasso regression. Lastly, for the linear regression model, the benchmark linear regression model is significantly better compared to the model we built, as it has a lower RMSE score. However, same as lasso regression, the linear regression we built has a better R-square score compared to the benchmark models. So for the comment on experiment that we attempt, the table above summarizes our experiment with random forest, lasso regression, and linear regression models. Each model was tested under 3 conditions: first, without modification; second, with hyperparameter tuning; and third, with robust scalar. For random forest and linear regression, robust scalar did not improve the performance compared to the baseline model. The best performance was seen in random forest without any modification and with only robust scalar. Lasso regression showed a slight improvement with robust scalar, but it was not significant. Random forest with hyperparameter tuning performed worse than the baseline model, possibly due to an overly large search space. As for hyperparameter tuning, it did improve lasso and linear regression slightly in MAE score, indicating better accuracy. In conclusion, this research aimed to build a machine learning model to predict crop yield. We conducted 3 experiments, one without any modification, one with hyperparameter tuning, and one with robust scalar. And the 3 models that we chosen are lasso regression, linear regression, and random forest. And overall, all the models performed well, but the modification did not significantly improve the performance. The baseline random forest and the random forest with robust scalar model had the best performance. Future research could explore more advanced deep learning techniques and assembled methods to further improve all of these models. Thank you. That's all from us.